So now let's look at an example of finding the length of a polar function. Let's find the length of the cardioid, r equal 1 plus cosine theta. So first of all, we have to understand what are our limits of integration, right? We weren't explicitly told what they were, but we know that the cardioid, recall, starts at, when theta is 0, you're at 2, so the biggest part's there. So now remember, you can plot those points to recall. But there's our cardioid. So to go all the way around, we'd have to go 0 to 2 pi. Actually, there's nothing special about starting at 0. You could start anywhere along that curve, but you want to make sure you end right back where you started. So I'm going to do 0 to 2 pi. And remember, length was integral from alpha to beta, our function squared plus the derivative of our function with respect to theta squared. And in this case, this is our function. So length in this case, like I said, I'm going to use 0 to 2 pi. I've got to make sure I go exactly once around. If I go more, I'm going to get more than just the length of that curve, right? I'll start adding more in. The function, 1 plus cosine theta squared plus its derivative, which is negative sine theta squared. Now, typically, we're hoping for some identities here. We've got sine squareds and cosine squareds. Let's multiply everything out. So what do we have? 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta. Sine squared plus cosine squared is 1. So we have 2 plus 2 cosine. Now, remember our strategy. This is good review for our integration strategy. With square roots, you're hoping to get a perfect square there. So because it involves trig functions, you've got to think through your trig identities. And is there an identity that involves a square that has anything that looks like what we have there? And the closest thing we have, maybe I'll just write it down here out of the way. Remember, that is close to being cosine squared, right? Cosine squared, we've been using this identity, right? 1/2 1 plus cosine 2 theta. I mean, it's got a constant plus. This is essentially 2 times that, or with the half, 4 times that, right? So let's try and manipulate this identity so it looks like what we have under the square root. So if we multiply through by 4, now it's looking a lot like that, right? 2 plus 2 cosine 2 theta, though. Well, the fact that the angle is not the same doesn't matter. What matters in this identity is this angle is double this angle. So if this angle is only theta, then this angle should be half of it, or theta over 2. So this should be 4 cosine squared of theta over 2. Yeah, as you read this direction, I guess, you start with this angle, 2 theta. You end up with half that angle. So here we started with theta, and we ended up with half that angle. So just altering that identity there. Now we've got a perfect square. Square root of 4 is 2. Square root of a square is the absolute value. Remember, be careful of that. That's an easy mistake. They don't cancel each other off necessarily, right? Square root of a square is absolute value. But as we run from 0 to 2 pi, we're taking cosine of 0 to cosine of pi. And from 0 to pi, cosine is never negative, so we can drop the absolute value. So I'll take the 2 out. And we're just integrating cosine theta over 2 from 0 to 2 pi. So when we integrate, we'll have to divide by a half, right, because of the 1/2 on theta there. So dividing by a half is like multiplying by 2. So this is going to be 4 times sine theta over 2 from 0 to 2 pi. Oh, you know what? I just misspoke there. This is good. I told you to be careful of this, and then I read right past it. Let's back up a second. First of all, let me show you what was catching my eye here in this. What was going to happen when I evaluated this? When I plug in 2 pi into there, I'm going to get sine of pi, which is 0. When I plug in 0, I'm going to get sine of 0, which is 0. And this is going to tell me that the length of this cardioid is 0. And I know full well it's not 0. So what did I mess up? I just said that cosine's never negative. That's not true. Let's look at the picture. What's cosine look like? I said we're going to be evaluating cosine from 0. Right? When you plug 0 into this, you get cosine 0. When you plug 2 pi into there, you get cosine of pi. So we're running from there to there. If this is, I'm just graphing cosine theta, not theta over 2. I just think of it in terms of the angles. So we're going from cosine of 0 to cosine of pi. Well, it's positive, and then it's negative, and it switches at pi over 2. But there's a certain symmetry here, right? I'm either going to have to do one of two things. The hard thing would be to break this absolute value up. From 0 to pi, this cosine is positive, so the absolute value could be dropped. But from pi to 2 pi, you couldn't drop the absolute value. You'd have to take the negative sign. So you'd break it up into 2 integrals. I don't want to do that. But because of the symmetry, I'm just going to take half of this and double it, right? Instead of going from 0 all the way around to 2 pi, I'm going to go from 0 to pi. So really, I'm just taking the length of the top half and doubling it. So at this stage, let's do that. So we're going to double this. We're only going to go from 0 to pi. But we're going to double it because we're only really doing half the curve now. But the symmetry, the top half is the same as the bottom half. So let's see what happens now. From 0 to pi, you're going from cosine of 0 to cosine of pi over 2. You're going from there to there. It is always positive. So now we're all good. So now when I integrate, we're going to divide by half or multiply by 2. This is going to be 8. And we're only going from 0 to pi. So now that's 8 times sine of pi over 2 is 1. Sine of 0 is 0. We get a length of 8, which is better than 0, right? This thing is definitely not length 0. So be a little careful. I just kind of blew right past that. I mentioned that you got to be careful about the absolute value. and then I totally said the wrong thing about those values, right? This thing, unfortunately, half the time this thing is positive and half the time this thing is negative. So there's no way to integrate that without either taking advantage of symmetry, which is the easier way, or recall what you would have to do here is two separate integrals. Let me just write that out real quick in case you were wondering. If you didn't have the symmetry to take advantage of, you'd have to go 0 to pi. Now from 0 to pi, you're going from cosine of 0 to cosine of pi over 2. The quantity inside is already positive, so it doesn't need the absolute value. But then you would have to add to that the integral from pi to 2 pi. And now the stuff inside here is negative, so the absolute value makes it the opposite. So now it's negative 2 cosine theta over 2 d theta. So you either would have to break this up into those two integrals, but really what those two integrals are going to give you are, the first one's giving you the top half, the second one's giving you the bottom half. And since there's symmetry here, these two things are going to come out the same, so you just get twice the first one, which is why we have 4 there. So be careful of that. I almost made that same mistake I'm always warning you about. So be careful. Square root of the square is an absolute value. And unfortunately, a lot of the examples in the book, they have rigged so the stuff inside is always positive. So if you forgot the absolute value, you'd be OK. But you can see we would have been in trouble here. We would have found that the length of that thing is 0, which is definitely not correct.